right, so today's topic, we're going to talk about joining, putting things together. We learned so far how to make things, at least the fundamental manufacturing processes. Now it's time to put them together. But the first question is, why in the first place we need joining or putting things together? And like always, I have a few examples, which like this year, I have to basically rely on whatever I have in my kitchen or at home. Let me switch my camera here. Okay, so this one, of course, is not in my kitchen, unless if I want to kill somebody. So this is a section of a saw, a circular saw. There is a reflection, so I try to move it like that. And the main body of the saw, it was part of a big saw. The main body of it is made out of steel, of course, tool steel, and the tips made out of tungsten carbide, basically, which is a hard material. And these two, of course, we cannot make with one material. Somehow we have to make them differently, like the blade itself, its thickness, it's about 3 or 4 millimeters. And then the tips, which has a particular geometry, you can see like here. And it has a different characteristic, of course. It's tungsten carbide, it's very hard. Unlike the blade, which is flexible, which we need sort of that ductility and flexibility to absorb vibration during cutting. And these two, we need to join them together. So here, absolutely, we need a joining process, which soon, like later in the lecture today, I'll explain how these things can be joined. It is by a process which is called brazing, which basically using another material between them and attaching them together, more like glue. But the glue here, you can think of it's a material. The main basically material is brass, but other alloys as well. That's one example. Another example that this one is really in my kitchen is a few years ago when I was in Paris. And of course, if you travel around the Eiffel Tower, you see a lot of vendors selling these scale replica of the basically Eiffel Tower, and it's metal basically. I'm not exactly sure, but what type of metal, but they say cast iron. It might be aluminum. I'm not quite sure about it. But let's see, what do you think can be the process to make this one, right? And keep in mind, this one is just cost, I believe, 7 or 8 euros. Still expensive, but 7 or 8 euros are considered to be relatively cheap. It's more like 12 or 14, let's say, Canadian dollars. So what do you think can be the process to make these? It's thin, right? And it's relatively a complex shape. Any guess? Let's see, we had machining. Of course, we cannot make it by machining. Powder metallurgy, well, no way, right? What else we can think of these? Any idea? Casting. So, Francisco, casting. What type of casting? Sand or die casting? Even casting can be complicated for this, right?
Yeah, I was actually thinking that maybe 3D printing is the best way of doing this, because there's just so many small holes in there.
Yeah, that's a good guess, 3D printing. But again, keep in mind, they produce this in mass production. 3D printing, especially, like I was there a couple of years ago, but like even 20 years ago, people were selling these. No, there were no 3D printing, and 3D printing for these can be very complicated. As you can see, we are stuck there, right? But the secret is, if you look closely, maybe hard to see from the camera, is Yeah, exactly, Kieran. As Kieran said, it's going to be with 3D printing very expensive and it's long process. So it's not 3D printing. If we look closely, we notice that this made out of 4 parts. Each side made out of, like they made them separately. Now each side by casting is very easy, right? If you want to make it in one shot with casting, it's almost impossible. So if you make each side by, let's say, casting, die casting easily can be done. Die casting is more like injection molding, but with metal. Then you can glue them together, weld them together, and make it cheap and easy to make it. Okay, so then it's also, so the second reason, or the second things that as this one, we need joining. This one definitely we need joining to make it cheaper. And another example, again, I found in my house is this toy. It's a gyro toy. Probably many of you guys maybe have it. In machine dynamics course, I teach gyroscopic moment, and probably in one of your courses you studied that as well. So the main structure, these 2 rings, and then the middle one is brass, so I can rotate it. I put a dot there so you can see it's rotating, right? It's a bearing in the middle, and it's very simple. So the outer rings, it's aluminum, and it's made by, most likely by powder metallurgy. The middle one might be powder metallurgy, it might be just machining. It's just a simple cylinder which has been machined inside, but it can be powder metallurgy. But let's say the outer ring, right? The outer ring, we need to make it out of 2 parts, and then we use fastening to join them together, right? Otherwise, making like these things, even the outer ring in one shot, it's going to be expensive. And beside, the assembly is going to be a headache, right? How we want to assemble these things if this is our one part. So now that we are here, let's play with it a little bit. It has nothing to do with this course, but just for fun. So this is the base, and this is the gyro. You know, there is no way that I can hold it there. There is no way that I can hold it, of course, there, right? It's not possible because even a little balance is going to fall off. If this thing is rotating, there is going to be gyroscopic moment, and hold it. Let me rotate it. So I have the motor. I attach the motor there, and I'm turning it on. So depends on how fast I want this one to rotate. Maybe good enough. Now it's rotating. It's difficult even to hold it. I can put it there, and it is stable now, right? You see? So, well, this is about this gyroscopic. And it can rotate maybe until our lecture is done, which we can come back and check it. So with that introduction, let me switch my camera back. All right, so I'm back. And all right, so with that introduction, I hope you guys are convinced that we need joining process. Is there any question, guys, so far? Are we good? Okay, let me share my screen then. And maybe I make this one small. I like this quote. When nothing goes right, go left. So if somebody have heard about it, do you know what's the meaning? Nobody have heard about it? Well, you should check it then. So joining process. Definition. Well, any like joining process is basically a general, let's say, terminology we use. It includes welding, brazing, and soldering, gluing things together like adhesive bonding, and also, why my picture is there, also the mechanical fastening, like the nuts and bolts, and even nails and screws consider part of the joining process. As you saw in these few examples, it is an important aspect of manufacturing. These are just few reasons. You can think of many, many more reasons, but the main one, sometimes some products are very complicated to make them as one part, unless we decide to go with additive manufacturing, which again, with additive manufacturing, we have our own limitation, and like time and expense is one big issue. So we want a simpler part, and that's why joining is essential. Economy, of course, if you make them individually, is cheaper. That's obvious. The third one, maintenance. That's a big thing. I recall many years ago, the car manufacturer that I used to work, we imported a car from Renault, France. And the car was relatively cheap. And we were like surprised how cheap the car is compared with all the function that it has. Then soon we realized that the way they manufacture the car is they join many parts together. So if, for example, a simple part need to be, let's say, changed for maintenance, if let's say it's broken, you need to change few other parts that has been attached to it. So in other words, the company was making money more from selling the spare parts and the maintenance rather than the car itself. But it was for a few years, because after that, customers start asking, okay, how easy it is for a car for its maintenance, and it is a big factor. So they go and check with the mechanic, and they say, oh no, don't go and buy this car, because if something happened to it, it's going to be expensive. So maintenance is one big thing. And different properties and functions, similar to the saw example that you saw, right? In the saw example, like this one, the tungsten carbide has one function, the blade has another function. So different material, different functions, they are made differently. Now you need to join them together. And transportation, of course. Sometimes you cannot, let's say, transport the whole machine or something to somewhere else. You need to make them separate parts, package them, and send them, right? So I believe it's very convincing that it is true. It is one important aspect of manufacturing. And of course, for you guys in this course, which you are learning the basic of manufacturing processes, you also need to have a basic knowledge in joining. But keep in mind, joining by itself, it's a full course. It's not even one. It's not, you cannot cover the material in one course. It's maybe 2 or 3 courses. Here we just want to give you a basic understanding, and it's pretty simple. So, but first, let's start with categories, the main categories of joining that we have. Let's say the joining process in general, if we want to categorize them, let's see if my pen is working. Oh, okay. So this joining process, I can break it down to 3 main categories. Let's do that. Because if you understand these categories, it will help you, let's say, either in future to sort of understand and follow how things are basically working, or which process you need to use when you need a joining process. let's say the first category, second, and third. So first we categorize them as like mechanical fastening. So mechanical. It's in a category of bolts and screws and nuts and nails. And then the second one is adhesive bonding. It's more like in category of glues and epoxies, which I'm sure you have used before. And then we go to the category of welding. So we have these three then categories. The first two are relatively straightforward, and but the welding, we can categorize welding to basically three main categories. So let me draw the things here. So the first category, we call it fusion. Like we fuse two parts together at interface. You can think of an interface of two parts, you melt two parts and then you attach them together. So they fuse together. So that's then the category of fusion. And the second category, let's call it solid state. So solid state, it's unlike the first category, the state of material doesn't change. Like the first one, fusion, you need to melt a portion of two metals. So the state is changed from solid to basically liquid, and then they fuse together. In solid state, there is no melting involved. And then we have the third category, which is brazing and soldering. So brazing and soldering, which involves a third material, which we use it as glue. But the glue here is, it's a metal itself. We melt it and we attach two things together. So let's look at this category. Let's look at fusion. So fusion, again, as I said, we melt an interface of two and we attach them together. So when we want to melt them, we need a source of heat. Based on the source of heat, we can categorize them in two categories, basically. So let's write here, based on, okay, that's not a good handwriting. Based on the source of heat, you can categorize them to basically chemical and electrical. So let's write here chemical and here electrical. So the chemical, we basically use a gas to make fires and to melting. So it is known as the type of gas we use. It is, or this process is, many people know now need as oxy-fuel welding. Like oxygen and another gas, which is either argon or another gas, which we'll talk about it in a moment, it's used as a main source for welding. For electrical, so electricity is the main source for heat, of course. It has three categories. And they are all in the category of arc welding. And these three categories of arc welding, they are All right, here. So one is the wire gas welding. Wire and gas welding. It's basically we use a wire to sort of transfer electricity to the part to generate heat. And we need also a gas, which the gas itself has a function, which I'll explain in a moment. And then we have in a category of tungsten and gas welding. And then the third one is electrode, no gas. No gas. All right, so this is like this last three. I will explain them in more details. Okay, for now, let's just focus on the categories. So they are, again, we use electricity to generate heat. When we use electricity, at the tip of that tool that we use to weld two things together, an arc is formed. That's why it is called arc welding. And sometimes we use basically a wire, which it is a consumable wire. This wire has been used to transfer electricity and it's being consumed. So constantly we need to feed the tool that we have for welding for this wire. Tungsten, it's considered to be non-consumable. Like if you have the tool for welding, it's gonna stay there. So it is then this tungsten, non-consumable. And then the last one, electrode, which we don't use any gas because it has a coating on top of it, and that coating, when there is heat, generates a gas to do the function that we want. And this is the most common, and most likely you've seen this sort of welding either here in the mechanic shop or maybe somewhere else. It's the most common welding process, and people use an electrode, which this electrode, again, consider a consumable. So if you heard about a consumable or non-consumable, basically welding tool, this is based on that main material we use. So this is all, as you can see, is in a category of fusion. Fusion, again, you melt, change the state at the interface, and then things bond together. The source of heat is either a fire, so oxy-fuel, or it's electricity, which has its own categories. And then we move to the solid state. Basically, the solid state, and there is no change in the state of interface that they want to like join together. Or if there is like a little, it's not like a huge change. It's like a small melting, like micro melting as interface, and then they join together. So this one also has two categories. Now things are getting a little messy. One trick that I can use, probably I can move the whole things here. Let me see, I can do that. Yeah, that's good. Okay. We'll go there. All right, now I have more room for this guy. Solid state. So solid state, let's break it down to two categories. One is mechanical. And another one is basically chemical. So again, don't forget, this is solid state. There is no melting. For mechanical, we have three categories. Do I have room here? I hope I so. Like, let's say category 1, 2, and 3. The first one is resistance welding. The second one is friction welding. And the last one is ultrasonic welding. All right. And chemical, there is just chemical. We use like a material or a material at interface that create the bonding, which is called diffusion as well, which I'll explain that in a moment as well. And the last one is basically brazing and soldering, which is similar to that circular saw example that I showed at the beginning. We join two metals together, and the interface is a third metal, which for soldering, we use solder, which is a thin lead metal. And for brazing, typically we use an alloy of brass, okay? So this is the main category. Again, as you can see, I spend quite a lot of time on explaining these because it's important to understand how you can categorize like basically welding process. And you might be surprised that maybe before this you thought, okay, welding is just welding, right? But you can see it has a lot of categories and a lot of science with it as well. Let's quickly review some of these technology so you get a sense of each. All right. So the first one, fusion, right? Fusion, again, we fuse two parts together by melting the interface. The source can be oxyfuel, right? Which this oxyfuel gas is a combination of oxygen and another gas, which the other gas is typically either acetylene, and of course oxygen is the other one. Argon also, some people sometimes use argon, but acetylene is the main one. So how does it work? We have a torch, right? Creates the fire, and we have a filler rod, because when we melt like two parts together, we don't want to melt it too much. We just want to melt the interface, so we use the filler rod. Sometimes people don't use the filler rod, depends on what they want at the end, right? And then we let it to solidify. Let's quickly watch maybe a demo. But from those links, of course, you can watch the whole things. Here is just
inspect your weld and continue practice. Rather than a push travel angle. The torch is tilted in the direction will be reversed. Begin.
So let me turn off the sound. Okay. So as you can see, the guy here, it has the wire and then the flame, the torch, right? And then it depends on if you're left-handed or right-handed. These blue things, if you can see, it's the flame, obviously, and then the filler rod. And you melt it, you make a pull, and then you join things together slowly. And hopefully you get this one. All right, so the process is simple. The second one is arc welding. Again, in arc welding, we use an electrode, which the electrode basically transfer electricity to the main metal, and it creates basically an arc. And at the same time, we use this gas. You see, like it's in the picture at the right, basically. We also use a gas. And this gas has a function. It creates sort of a cushion around this fire to protect this area, because the temperature is high and the chance of oxidation is high. So it's basically protect that area of welding from contamination. Let me quickly show a demo for that. Arc welding. And before that, as I said, you can either use a consumable wire or like tungsten, which is a non-consumable wire. The source of electricity can be DC, constant, basically electricity, or alternative electricity, which the AC is preferred because this changing basically the amplitude, it clean and remove oxides from the area for welding. Maybe go to one of these demos.
In MIG welding, thin wire acts as the electrode.
Okay.
This wire is fed from a spool mounted on a gun or inside the welding machine through a flexible tube and out of the nozzle on the welding gun or
Start
torch.
from the beginning.
In MIG welding, a thin wire acts as the electrode. This wire is fed from a spool mounted on a gun or inside the welding machine through a flexible tube and out of the nozzle on the welding gun or torch. The wire is fed continuously when the trigger on the welding gun is pulled. When this trigger is pulled, it also switches on the welding current and a shielding gas. An electric arc forms between this wire electrode and the workpiece and heats both metals above their melting point. These metals mix together or coalesce and solidify to join the workpieces into a single piece. The metal in these parts to be joined is called the base metal, and the metal that comes from the melting wire electrode is called filler metal. MIG welding always adds filler metal to the joint. Because the wire electrode melts as it's being used, MIG is called a consumable electrode process. What is TIG welding? TIG stands for tungsten inert gas welding. The American Welding Society calls this process gas tungsten arc welding, or GTAW. You might also hear it called Healy arc welding. TIG welding uses a tungsten electrode. Tungsten has an extremely high melting point. When you TIG weld, the electrode gets hot, but it doesn't melt. We say that it's a non-consumable electrode. That doesn't mean it lasts forever. That just means that it doesn't melt and become part of the weld. It works by melting the base metal, and that is the metal that makes up the two pieces that are to be joined. The heat is generated by an electric arc that forms between the base metal and the tungsten electrode. Now, you can TIG weld with or without filler metal, and that's not a choice you have in a lot of other processes. If you want to add filler metal to a TIG weld, use a filler rod, which is just a rod of metal with a specific alloy. You want to make sure that the filler metal you're using is compatible with the base metal and that it has the strength required to do the job. In TIG welding, the molten metal is protected by a shielding gas. This gas, usually argon and sometimes helium or other gases, keeps the molten metal from reacting with oxygen, water vapor in the atmosphere.
All right. So nice, basically summary of the arc welding with either consumable wire or non-consumable wire, which is tungsten. And please watch this video because I just showed a portion of it for a little bit more details. And now this in the same category, but this time we use an electrode. And the only difference between this category and basically the previous one, like the wire, consumable wire one, is instead of using an inner gas, basically, like if I step back one slide, here we had like this inner gas, right, coming out to provide this shielding, we said shielding gas, as you heard in that video, for protection. Now this gas is being produced on this image on the right, on this schematic, is going to be produced by this coating, like the coating on the surface of this electrode. It's called flux, and this flux, when it is under heat, it's going to basically create like this gas that we want for protection, this shielding gas, and it's considered to be consumable, right? And usually this coating is it's a flux which made out of different material, like carbonate or silicate, basically materials, which again you don't need to, but if you are interested, you can find on internet and study those in details, what these electrodes are made out of. And this is again one of the most common welding process. And here in our mech shop, if students for their capstone, not this year, but previous years, I've seen many of the students doing this welding. But of course, you need to learn how. It seems easy, but it's not really that easy. And now the question is, what materials can be welded together? So in simple words, all of the ferrous material can be welded. All the category of steel, like low, high, medium, Stainless steel, they are generally weldable. Cast iron also is weldable, right? And for non-ferrous material, aluminum alloy considered to be weldable. Only things that you need to be careful, if in aluminum alloy there is zinc and copper, basically they consider not to be weldable. And the main reason is because copper and zinc, they are not really mount to any other material. There is not going to create any bonding. So if there is zinc and copper, it's going to prevent that bonding, basically. So copper by itself, like if you have copper to copper, you can do that. Magnesium also can be welded, but it's important, the protection, like the shielding gas is an important thing because it can be oxidized very fast. Nickel alloys, similar to stainless steel, and tungsten and titanium as well, they are weldable, but you need higher heat, of course. That's why nobody use welding, like fusion for, let's say, again, going back to the example of this saw, to attach tungsten carbide to the main blade. We need another process because you need a lot of heat to melt it. Moving on, we go to the second category. So the first category, again, was fusion. The second was solid state. No change in, no melting involves. There is a little bit of welding, but it's a small scale. You don't change the shape of that interface, such as the fusion that you saw. We can categorize them to mechanical, electrical, and chemical. And the main base for these categories is what is the source of heat? Because still when we want to, in solid state, when we want to attach or join two things together, still we need heat to create that maybe micro, let's say, or nano plastic deformation or plastic or plastic melting a little bit in nanoscale so things can bond together. So in mechanical, we have three categories: ultrasonic cold welding, which is, in fact, there is no heat involved, ultrasonic and friction. And then we go to the second category, which we use electricity, which is called resistant welding. And for chemical, it is called diffusion bonding. Let's take a look at each. Cold welding, as the name implies, there is no fire, there is no heat involved, no electricity to generate heat. And we press things, in fact, together, like these two rollers. We see these clothing, basically it's called cladding metal, which is the cover or the clothing metal, and the base metal. So it's typically good when you have, let's say, this category of ABC at the bottom that I said. You have, let's say, pure aluminum, and then you cover the hardened aluminum alloy to protect it. The same for stainless steel, like category of B for mild steel, or couple for cables, for some coaxial cables. Like the inside is steel and the outside is basically copper. This is a common method to join things together. Again, for this, you can think of it more like you use force to press things together. All right. Moving a little faster, ultrasonic welding, it's called ultrasonic. And the main reason is because we use basically the frequency that we use is it's over the frequency that human can hear. So human frequency is in a range of 5 to 20K. So human, basically ear frequency, it's a range of 5 to 20K hertz. But this is above that. As you can see here, it's range of 10 to 75, very common 30,000, like 30K hertz. What frequency we are talking in this schematic? As you can see, we have, let's say, this yellow and this green, two different basically plates. We put them on top of each other and we use this actuator and this transducer, and it creates a very fast motion. And these two layers basically slide on top of each other, and there's gonna be a shear stress between them. This shear stress generates a heat, and again in a nano scale and in this at interface creates maybe a, let's say, a very thin melting area which these two join together. Okay, so that's basically the whole idea. Very similar to that is friction welding, which the idea is again the same, but instead of basically fast motion of two parts on top of each other, now it's more like rotation. It's usually good for when you want to attach two shafts. Like as this schematic shows, picture 1, we want to attach these two bars together. So we apply a force while one of them is rotating very fast. And because of this friction, is going to be a melting happenings at the interface, and these two will let it solidify and these two join together. Let's look at a quick demo. So as you saw, it's high-speed rotation and there is friction. Still, there is melting involved at interface, but it's not really too much. However, for this one, it seems looks like too much. And then this basically flash at the end, we need to machine to remove it. All right. Moving on, it's going to be resistance welding, basically. Again, let's look at this schematic. 1, 2, 3, 4, and 4 steps. Two parts on top of each other. We apply a force to clamp them together. Current pass through these two electrodes, which on this image, like at the bottom, you see these are the electrodes. And because of these like electricity or current between these two electrodes, we can say like in the middle, not the whole thing, we are going to have an area which start melting, right over here. And but again, it's not too much. They control it so the melting doesn't get to the outer surface. It's more like around this area, which is called nugget. Let's take a look at another demo for this one.
Resistance welding is a process where metal parts are squeezed between two weld tips. Current flows between the weld tips and encounters resistance at the weld tip interface and at the part interface. Resistance to the current at the part interface creates enough heat to melt the metal and cause a weld nugget to form. The heat at the weld tip interface is conducted away by the water-cooled weld tips while the part interface continues to get hotter and hotter. About halfway through the weld time, the metal at the part interface begins to melt, then a weld nugget is formed. When the weld time is complete, the current stops flowing. Then a hold time of approximately 4 to 5 cycles is used to give the weld tips enough time to absorb heat from the outer perimeter of the weld nugget and cause it to harden before the weld tips open. A weld nugget should be as wide as the weld tip that contacts the thin metal and penetrate to between 20% and 80% of the metal thickness. This is referred to as a setup nugget. To produce setup quality weld nuggets, you need to understand how resistance welding is affected by weld tip alignment, weld tip force, squeeze time, weld tip size, weld current, weld time, weld tip cooling, and hold time.
So keep in mind then these 8 parameters to control these, basically the nugget, right? The weld nugget, right? There are 8 parameters. That's from the time, the thickness of the material, the amount of current, and so on. And the whole video, of course, you can watch for more details. Each of them is 2 or 3 minutes, but I just show you here a section of it. So the resistance welding, there are again 2 types of machine, or 2 main categories. One is called the spot welding, like the machine, as you can see here, it at like individual spots create the welding. While another one, which has this rolling, it's called seam welding. It's more like seaming process. It's continuous welding, and like unlike the previous one, which you have these 2 electrodes, they come close to each other and create like a point. Basically, these 2 rollers, they are continuous. And you see here on the picture C, a weld nugget at points, right? Maybe because these basically roller, the current was stop and on. So it depends how we want it. Or maybe we want it like a continuous welding. Let's take a look, another quick demo.
What's the water tube for?
So that's a good question. The water tube is to basically make the solidification faster, right? And also with this one, we remember the video, the previous video that we watched? At some point, the guy says we need to have like a coolant, basically, to make the surface, basically to remove the heat from the surface, because we want the heat to be like in the meat, in that nugget, right? And here you see the application of seam welding is vast, basically for the pressure vessels and tanks. So next time when you're drinking your beer, you know, those like tank made like by this process. Right, basically all the pressure vessels and like brewery tanks, they made by like seam welding. And diffusion welding, which was in a category of, again, using chemical material basically to create that interface, the bonding basically. So in matter of time, because we are short in time, I'll leave you guys to watch the demo for this one yourself. And let's take a look at the last one, which is last 2, brazing. Brazing and soldering, 2 materials. We melt basically the interface. So the interface, whatever material we use for that, is going to be melted, not the base. Like again, referring back to the example of this saw, the tungsten, the tip, and the blade, there's not going to be any melting for them. The interface, which is brass, is going to be melted, and you can think of that as more like glue. So this is the brazing process, and I guess I have a quick demo. And this is the last one, basically.
You can also join both similar and dissimilar metals, thick or thin sections, and metals that have widely different melting temperatures. So brazing gives you plenty of material options. Another reason brazing is so popular is because it's economical, easy to do, and produces a strong joint that won't leak. Having a leak-tight joint is critical for HVAC applications because they are closed systems with liquid or gas as a heating or cooling medium. If there are any leaks, liquid or gas can escape and prevent the unit from functioning correctly. Now let's take a look at the nature of the brazing process. What exactly is brazing? Brazing is a method of joining two pieces of metal together using heat and a filler metal. The joint area is heated above the melting point of the filler metal, but below the melting point of the metals being joined. So as you heat the base metals, the filler metal melts and flows through the entire joint through capillary action. As the joint cools, a strong metallurgical bond forms between the filler metal and the two base metals. Brazed joints are incredibly strong and can be made with lower heat and will generally be stronger than the metals being joined. You could almost say a brazed joint makes itself in the sense that capillary action is responsible for flowing the filler metal completely through the joint.
Right, so that's for brazing. Soldering, I'm sure at some point in your life you've done some soldering, hopefully. It's very similar to brazing, but it's more for electrical wires and electrical boards and so on, because the bonding is not that strong like brazing, but the concept is the same. And as you know, instead of a flame, and typically we use basically a soldering iron, right, for generating the heat. Glue, I'm not going to talk too much about glue. So you have used glue hopefully at some point in your life. It can be in different form, liquid, paste, drops, like droplet, tape and film and so on. The bonding can be like chemically reactive, like epoxy, or pressure sensitive. When let's say you use a rubber and as the glue, rubber base basically. And it's more like under pressure, things can join together. Or it can be hot melt, like hot glue, which most likely you've heard about it. And the last things, fastening, the easiest, the best, cleanest process to join things together. Whenever it's possible, we'd better use mechanical fastening, bolts and nuts and screws, which has its own category and story for itself. And rivets, of course, which again, either you have used or you have seen. All right, that's it, guys, for today. I guess if there is no more questions, see you guys later. Not later. I'll see you on Thursday. And good luck with those of you who have exam today.
Thank you.
Bye. Goodbye, everybody.